Okay, let's get started. I hope everyone's doing well. We'll try this out, see how this goes. So what we'll do today is we're going to discuss stereochemistry in more detail. Okay. Now, last week when we talked about stereochemistry, or when I introduced you guys to this topic, what we did is we talked about achiral and chiral objects, molecules. So we talked about the concept of achiral and chiral molecules or objects. And what we said is achiral objects or molecules are the one that are superimposable on its mirror image, whereas chiral molecules are the ones that are non-superimposable on its mirror image. And now for chiral molecules, what we did is we actually worked through for molecules, okay, for molecules, when this is applied to molecules, we worked through carbon atoms. We looked at carbon atoms which have different kind of groups connected to them, like carbon atoms which had three identical groups, carbon atoms which had two identical groups connected to them. And what we realized, or what we kind of arrived at, was that a carbon atom connected to four different groups is needed for the kind of molecules that we were talking about. Realize there are mentioned that there are other higher order things that we will not go into, but for everything that we are talking about, we are referring to carbons that are sp3 hybridized. Okay, so those are the carbons that we are talking about here. And this carbon atom, the carbon atom that's connected to four different groups, is called a chiral center. Okay, and that is kind of key for a molecule to be chiral by itself. But also realize that we talked about mesocompounds. Okay, these are achiral molecules which contain chiral centers. So the presence of a chiral center does not guarantee that a molecule is going to be chiral. Okay, that's just one of the things that we look for. If a molecule has a chiral center in it, then chances are that it's going to be, or at least it has the being a chiral molecule. That does not guarantee that the molecule is going to be chiral, because there are mesocompounds which contain chiral centers, but the molecule itself is chiral. And what we talked about later was that mesocompounds, they are achiral because they usually have a plane of symmetry. So the plane of symmetry is what makes a molecule achiral. And the same applies to objects as well. What makes an object achiral is the presence of a plane of symmetry in the molecule, or in the object, I mean. Okay, so an example for a mesocompound, could be a cyclohexane. Okay, but let's say this is a dimethyl cyclohexane. Now this cyclohexane here has two chiral centers in it, but this molecule also has a plane of symmetry. So there's an internal plane of symmetry which basically cuts the molecule into two identical halves. two identical halves. And for that reason, this molecule is going to be achiral, and we'll call this a meso compound. Okay, so that was the kind of the preface, like the discussion that we had last class. Now, moving forward, what we're going to do is we're going to talk or discuss a little bit more about other stereoisomers that are possible. So we talked about stereoisomers also, like last chapter. We saw cis and trans isomers as one possible kind of stereoisomers. What we're going to do now is talk about enantiomers. So enantiomers are another kind of stereoisomers. So we'll talk about what enantiomers are. So if we consider, or maybe we can define them first. So enantiomers are molecules that are related to each other as non-superimposable mirror images. So if there are two molecules that are related to each other as non-superimposable mirror images, then those are called enantiomers. So for example, let's consider a simple molecule here. So if we have this molecule, okay, so it's an alcohol. It has a hydroxyl group in it. So if for this alcohol, realize that we have a chiral center in this molecule, because when we look at that carbon, this carbon is connected to the hydroxyl group, it's connected to a methyl group, and it is connected to an ethyl group. And then additionally, it has a hydrogen, which is not shown, which is going on the dash. So there's a hydrogen. So the carbon has 4 different groups connected to it. So this is a chiral center. Now, if I were to place this molecule in front of a mirror, reflect it, so if the mirror is right here, so orthogonal to the plane of the whiteboard, and if I reflect this molecule in that mirror, what I'm going to see is something like this. Okay, this is what I'm going to see in the mirror. So this is the mirror image. So we have a molecule with a chiral center. We've drawn its mirror image, and now realize that these two mirror image, the molecule and its mirror image, the two molecules here, they are non-superimposable on each other, because if I take the molecule out and then try to overlay on this molecule, we are going to run into problems, because on the left here, we have an ethyl group, but on the left here, there is a methyl group, and the same thing on the right. Now you might think that, okay, I can take this molecule and just flip it over so that the ethyl group overlays with the ethyl group and the methyl group overlays with the methyl group. But then realize that in our starting molecule, the hydroxyl group is on a wedge. So it's pointing outside the plane of the whiteboard. But if I take this molecule and I flip it over, that would put the hydroxyl group in that molecule behind the plane of the whiteboard. So we're not going to have an overlap here. They will not superimpose, or they are non-superimposable. Okay, so these two molecules are going to be non-superimposable. And so since these two molecules are related to each other as non-superimposable mirror images, they are enantiomers of each other. These are enantiomers. I need the off. So these are enantiomers of each other. So enantiomers are essentially molecules that are related to each other as non-superimposable mirror images. Now we can look at another example. So consider a molecule like this maybe. So let's say if we have a benzene kind of a ring or a phenyl ring, and I have a molecule where there is a chloro group on that benzene ring. I can take this molecule and I can again draw a mirror image. where the mirror image is going to be this molecule here. And again, this carbon is chiral because it has 4 different groups connected to it, and we cannot superimpose these mirror images. So these 2 molecules would also be related to each other as enantiomers. Now, one thing that I want to point out is the mirror image that you draw, really depends, like the structure of the mirror image that you draw really depends on where you consider the mirror plane. What I've been doing is I've been considering the mirror plane in the middle, orthogonal to the plane of the whiteboard. So it's orthogonal to the plane of this whiteboard. But I could consider a mirror in front of this molecule. Okay, let's say if there is a mirror here in front of this molecule, then the mirror image that I'm going to see, okay, then the mirror image that I'm going to see is probably going to look like this. Not probably, it's going to look like this. Okay, so then the mirror image that I see should look like that. Because what I've done is I've put a mirror in front here. And so the phenyl ring would be there. The methyl group would be showing up at the same spot. But now the chlorine is actually pointing inside. So when I reflect in a mirror, the chlorine in the mirror image should be on the outside. So it will end up on a wedge. So these 2 now, in some sense, are the same molecule, because if I take this molecule and if I flip it over, the phenyl ring would end up on the left-hand side, the methyl would go to the right side, and the chlorine would end up on a wedge. And that's what we have here. So there is no rule that you have to reflect it on a mirror that's perpendicular to the plane of the board, or in your case, the plane of the page. It is any mirror. As long as you reflect it on a mirror, whatever you get it is a mirror image. So for example, if I'm standing here and there's a mirror right here, I'm going to get a mirror image of myself. But if there's a mirror here, I'm going to get a mirror image of me there. And it's here, I'm going to get a mirror image there. Or my backside, there's a mirror image over there. So it really depends on the perspective and where you're placing the mirror. But these are both mirror images of the same molecule, So these are both the same, and they're mirror images to this molecule, just drawn from different perspectives. Okay, so we talked about enantiomers. So enantiomers are essentially non-superimposable mirror images of each other. Those molecules are called enantiomers. So that brings us into something more important now, and to some extent, more interesting as well. Okay, we're going to draw another molecule. So let me give you an example. Okay, so I have a molecule here. Let's draw a mirror image for that molecule. So let's go ahead and try that. I've given you a molecule, and we're going to draw a mirror image for that molecule. So you might want to start off by identifying how many chiral centers there are. That's a good question to ask. And if you look at it, this carbon here has 2 methyl groups attached to it. So this is not a chiral center. This carbon here has a chlorine group. It has a methyl group. And then there is this isopropyl group and then a hydrogen. So that's our chiral center. Okay, so that's our chiral center. So if I draw a mirror image for this molecule, I should get something that looks like this. That would be the mirror image. Okay, so that's the mirror image of the molecule. And these 2 mirror images are non-superimposable. So they're enantiomers of each other. So these are enantiomers. Okay. Now let's go ahead and do another thing. Let's go ahead and name these molecules. Okay, let's go ahead and name these molecules. So if I had to name this molecule, I want to get the longest carbon chain. Okay, and then we want to put the substituents on the lowest positions possible, the lowest number of carbons possible. So since we have 1, 2, 3, 4, you can see that this is 1, 2, 3, 4. So there's a chloro group or a chloro substituent on carbon number 2. There's a methyl group on carbon number 3. Alternatively, I can start counting from here. That'll give me 1, 2, 3, 4. So the substituent locations are the same, but then I will get the methyl group on carbon number 2, and the chloro would be on carbon number 3. So we're talking about a number scheme like this. So this is the other option. So we can go 1, 2, 3, and 4. Now you could go 4 up, or you could make that one. That doesn't really make a difference. Okay, so when we look at this here now, if I count from the right, that gives me the opportunity to put the chloro group on carbon number 2, which is the lower number, and the methyl group is on carbon number 3. But if I go from the left, then the methyl group is on carbon number 2, and the chloro ends up on carbon number 3. So since we have the opportunity to put the chloro on carbon number 2 counting from the right, that is what we will do. So we can name this compound as 2-chloro 3-methyl, 4 carbons is butane. I'm going to take away that definition from there. So these are enantiomers. So this is a 2-chloro 3-methyl butane. Now, I can name this compound, and what you would realize is when you name this compound, this is also going to be 2-chloro 3-methyl butane. So they both have the same name, which makes sense because they have the same connectivity. Every atom is connected to the same other atom, so they have the same connectivity also. But then that raises a very important question. Then if I say, or if I ask you to draw 2-chloro 3-methyl butane, what is it that you're going to draw? Because they are both 2-chloro 3-methyl butane. But earlier we also said that these are enantiomers of each other. They're not the same molecule. They're related to each other as non-superimposable mirror images. So what that means is we have to add probably another element of detail to this nomenclature. There's something else that's missing in this name, which would tell me whether I'm talking about the molecule on the left or I'm talking about the molecule on the right. So we'll learn that. So how to assign that, okay, that is given by the Kahn-Ingold Frelog nomenclature. Okay, that's how you assign the name or the new notation that we're going to learn. And what this defines is what we can call the configuration. It defines the configuration of the molecule. Now, the configuration specifically is for the stereocenter or the chiral center. Okay, it's for the stereocenter or the chiral center, because what the configuration means is it is the configuration, okay, the configuration is the 3D arrangement of groups around a chiral center. That is what the configuration tells us. It tells us the 3D arrangement of groups around the chiral center. So there are some rules to do this, and we will talk about that next. And we'll go back to these molecules. So what the rule says is, or the nomenclature rule says is that when you have a chiral molecule, and there's a chiral center in your molecule, what you're going to do is you're going to assign priorities to the groups that are connected to the chiral center. So let me take away some of this numbering scheme from here. Okay, so we're going to assign priorities to the groups that are connected to the chiral center. So in this particular case, if we think about it, we said this earlier, we have a chlorosubstituent, we have this isopropyl group, we have a methyl group, and then the hydrogen group. So what we're going to do is we're going to assign priorities to these 4 groups. So, and these priorities are assigned by atomic weight in some sense. So do not look at how big the group is. The atomic weight is important, okay? And I'll walk you through a few problems just to show how we do this. Okay, so if I look at this carbon, the chiral center, the atoms connected to the chiral center, and we're looking at the atoms that are directly connected to that chiral center. So if I look at it, this carbon, the chiral carbon, is connected to a chlorine, it's connected to a hydrogen, there is a carbon, this is a methyl group, but the chiral center is connected to a carbon, and that carbon is connected to 3 hydrogens. So we are only looking at the atoms which are directly connected to the chiral center. So the chiral center here is connected to a carbon, and there is a carbon over here, which is connected to other atoms. So among the atoms that are directly connected to the chiral center, if we were to prioritize them based on atomic weight, what we would see is that hydrogen is the least priority, that is the smallest or the lightest atom in terms of like atomic weight. So hydrogen is the lowest priority group. So hydrogen will be assigned a 4. Chlorine, on the other hand, it is the heaviest atom that's connected to the chiral center. So that would get 1. That will be given a priority of 1. Now, apart from those 2, we have 2 carbon atoms. So they're both carbon atoms. And so what that means is we cannot assign a priority to them yet. So we have to do more work. We need to look at their surroundings now. So what we're going to do is we are at these carbon atoms. So now we're going to go beyond those carbon atoms. This carbon atom here is connected to 3 hydrogen atoms because that's a methyl group. This carbon atom here is connected to 1 hydrogen, and it's connected to 2 carbon atoms because these are methyl groups also. So when we look at this carbon versus that carbon, this carbon is connected to 3 other hydrogen atoms. This carbon is connected to, the carbon on the left is connected to a hydrogen, and it's connected to 2 carbon atoms. So as we move beyond, what we see is this carbon on the left has a higher priority because it is connected to heavier elements. The carbon on the right is only connected to 3 hydrogen atoms. So what we're going to do is we're going to give this a priority of 2, and the carbon on the right gets a priority of 3. This could be confusing right now, but we're going to look at a few more examples, and that would hopefully help you get what we're talking about here. Okay, so once we've assigned the priorities, to all the groups, okay, so the first thing what we did here is we have assigned priorities to the 4 groups connected to the chiral center. That's the first thing what we did. Now that we've assigned priorities, what you do is you orient the molecule. You orient the molecule such that the lowest priority group, which is the hydrogen atom here, is facing away from you. So it should be like away from you. Now, luckily in this particular structure, the hydrogen atom is on a dash bond. It's on a dash. And what that means is it's going behind the plane of the whiteboard here. And so when I look at it from here, the hydrogen atom is already pointing away from me because the chlorine is on a wedge, it's pointing towards me, and the two carbon atoms are on straight bonds, so they are in the plane of the whiteboard. The hydrogen atom is what's behind the plane of the whiteboard. So it's already pointing away from me. So that's a good thing because now I don't have to work a lot for this. But we'll look at some other examples where the hydrogen atom or the lowest priority group may not be pointing away from you. Okay, so now this is pointing away from us. So place, or not place, I think orient the molecule such that the lowest priority group is away from you or the viewer. Lowest priority group is away from you or the viewer. And now that we've done this, what we are going to do is we're going to go from the group with the highest priority to the group with the third highest priority. So we go from 1 to 2 to 3. So 1, 2, and 3. So we're kind of ignoring 4 right now. That's away from us. We're kind of ignoring 4 at this point. And now in going from 1 to 2 to 3, we are doing a counterclockwise rotation. So if we do a counterclockwise rotation going from 1 to 2 to 3, then we assign this chiral center as S. So we call that this is an S chiral center. It's an S chiral center. Okay. Let's go to that other enantiomer and see what happens in that case. Now, once I've assigned priorities and I've done all of this work here, I do not have to redo that work for this other enantiomer. All I have to do is just transfer the priorities from this structure to that structure. So chlorine is 1, hydrogen is 4, this carbon is 2, and the carbon on the left is 3. So assigning the priorities is done. Molecule is already oriented such that the lowest priority group is away from us. And so I'm going from 1 to 2 to 3, we moved clockwise. So this is a clockwise rotation. This is a clockwise rotation. And in this particular case, we call this chiral center to have an R configuration. So the R and the S refer to configuration that we talked about earlier. And so now once we've assigned the configuration to the chiral center, this is R, this is S, what we do is we can go ahead and include the R and S in the IUPAC name of the compound. So for this particular case, we can say this is an R 2-chloro-3-methyl-butane. And for this particular case, we can say it's an S 2-chloro-3-methyl-butane. Now, another way to write this name, okay, a slightly different way to write this name would be to write it as 2R chloro 3-methyl butane, and this would become 2s chloro 3 methyl butane. Now, essentially what we are doing here is we are specifying where is our chiral center. So our chiral center is carbon number 2 on the longest carbon chain. And we're essentially saying that that chiral center is of the R configuration. Or we are saying that the chiral center here on 2 is of the, sorry, my bad. That's not R. This one is S. So this is S. And this is R over here. I'm pretty sure if we were in class, some of you would have pointed this out by now that I messed up. But this one is RS, that one is R. So this is the S configuration, that is the R configuration. So we can write it as 2R chloro 3 methyl butane. So what we're trying to say is the chiral center is on carbon number 2, and the configuration about that chiral center is R. That is what this name suggests. Now, if there is only one chiral center in your molecule, you don't have to really put it by the number of the carbon. You can just put it outside, it's fine. But in a situation where molecule has more than one chiral center, it is very helpful. In fact, that is the norm, that you actually put the configuration next to the location, so that you can know that, okay, my second carbon is of the R configuration, and maybe my fourth carbon is of the S configuration or the R configuration, whatever that is. So doing that is really helpful. Okay, let's go ahead, try another example. Okay, we'll try another example here. Okay, so we're doing RS configuration. This is what we are talking about right now. And let's choose an example. Like that, maybe. Maybe that's the, in fact, what we should do is, I think we're going to put it on a dash so that we see what happens when you have a different configuration. So in this particular case, again, we have our chiral center here. And we have another chiral center in this molecule. So maybe this is not an appropriate example for now. I think we'll skip this. Let's do away with that. Let's get rid of that. That'll be too complicated. Okay, let's try that. I think that should be fine. So let's try that. Let's see what we get for this molecule. There's only one chiral center in this molecule. And we can draw its mirror image, which should be this molecule here. Okay, I know they don't look like mirror images. That structure is much bigger, but you know, they're mirror images of each other. They're drawn as mirror images. So that's our chiral center. Now for this molecule again, so if we start doing or going through the protocol, the first thing what we're going to do is we're going to assign priorities to all the groups. So on the chiral center, we have an oxygen, we have a carbon, and a hydrogen. So of all of them, the hydrogen is the lowest priority, and the oxygen is going to be the highest priority. Oxygen's atomic number, mass, is bigger than that of carbon. So it's a heavier element compared to carbon. So that's 1, this is 4. Okay. Now, between these two carbon atoms, there's a tie. So we look at what else is the carbon connected to. So this carbon here is connected to 2 hydrogen atoms and another carbon atom, whereas this carbon here is connected to 1 hydrogen atom and 2 carbon atoms. So this carbon is connected to 1 carbon atom, 2 hydrogen atoms. This carbon is connected to 2 carbon atoms, 1 hydrogen atom. So based on the weight of the atoms connected to those carbon atoms, this one's going to win. So this is a 2 and this is priority 3. Okay. Now, the next thing we have to do is we have to orient this molecule such that the lowest priority group is away from us. So what we can do is we can take this entire molecule. So I can simplify this molecule as this. So there's 3, there's 2, so there's 3 on the left side, 2 on the right side. 4 is on a wedge, 1 is on a dash. And I need to orient this molecule such that 4 is pointing away from me, so behind the plane of the whiteboard. How do I do this? If I take this molecule and if I flip it over. So essentially, if I take this molecule and if I do a 180-degree flip, so essentially we're doing a flip about an axis like that. We're basically flipping it over. If we do that, now this molecule, after I do the 180-degree, 2 is going to end up on my left-hand side, 3 would be on the right-hand side, 4 will go in, and 1 would come out. So now we placed 4 away from us. And then in going from 1 to 2 to 3, we do a counterclockwise rotation. So this molecule is an S configuration. Okay, we did a counterclockwise rotation. So this molecule is an S configuration. Now I'm going to show you another thing that you could do where you could avoid doing this flip. So the way this molecule is right now, the lowest priority group is pointing towards me. It's pointing towards us. It's not away from us. So one thing we can do is we can just ignore that group for now. Just ignore it. And then what you do is you basically see how does it move, like what's the rotation in going from 1 to 2 to 3. So in going from 1 to 2 to 3 in this structure, I am doing a clockwise rotation. So a clockwise rotation would mean the R configuration. But there is a problem. And the problem is the lowest priority group was pointing towards me. And so because it's a clockwise rotation or an R configuration when the lowest priority group is pointing towards me, what you can do is you can just flip the configuration. So this rotation looks like an R, but because the lowest priority group was pointing towards us, what we can do is we can flip the configuration and the right configuration is going to be S, which is what we got here. Okay, let's go ahead, try it out on the other structure here. So we have 1 hydrogen on the wedge is 4. This is 2, and that's 3. So again, the way the molecule is drawn right now, it is 3, 2, 4, and 1. If we consider an axis and do a 180-degree rotation about that axis, what we're going to get is 3, 2, 1, and 4. And now in going from 1 to 2 to 3, this is a clockwise rotation, which means this is R. And now you can try the other thing here. So if we ignore 4 over here, ignore the hydrogen, the lowest priority group, in going from 1 to 2 to 3, we are doing a counterclockwise rotation, which is S, but the lowest priority group was facing towards us. So although it comes out on S, this should be an R, which is what we get here. So that way we are able to like assign configurations to these molecules. And this is very useful. We can do it for molecules with more than one chiral center, and then we can go from there. So what we'll do is we'll stop right here. This is one part of the video, and then I'll continue on with more material in the next part.